All right, chemistry class, we are going to continue our discussion about chemistry here, and in this section we are going to be looking at reaction rates, and to go along with that, the topic of equilibrium. We actually have talked a little bit about equilibrium already when we were looking at phase changes and such, but we're going to be looking at that again a little more in detail, along with how quickly reactions occur. That's what we mean by reaction rates. Okay, so in your notes, if you would please first put down reaction rates, the rate of a reaction. That's also referred to as the kinetics, or the speed. Kinetics is movement, motion. In order for reactions to occur, there has to be particles that are moving and colliding. Okay, so reaction rate is what we're going to look at first. What I'd like you to know about this is, in order for a reaction to occur, there are basically two things that you need to know right here. So point A is molecular collisions. Actually, there's really three things that have to happen. Okay, first thing has to happen is there has to be a collision. So molecular collisions, particles have to collide in order for there to be a reaction. So that's the first thing. Okay. Then, once there is a collision, they have to collide with the right amount of energy, enough energy when they collide in order for bonds to be broken. That's the second thing. And then the third thing is they have to collide with the right orientation. That's to kind of hit at the right angle, if you will. So, three things have to happen. First, they have to collide. Particles have to bump into each other. They have to slam into each other. And then if they do, they have to slam into each other with enough energy, and then they have to hit each other with the correct orientation, hit each other just at the right angle. So you have to know those three things: collision, enough energy, and the correct orientation or angle. Okay? That's what we call collision theory. So if you want to write down collision theory, that's the idea there. Okay? They have to collide with enough energy and the correct orientation in order for the chemical reaction to occur. That is critical. Now here we have a general chemical reaction. Notice we have AB, and AB is representing a compound. A is some element. It's actually just a make-believe element. B is a different element, again make-believe, and it's going to collide with another AB molecule. So we have an AB molecule and another AB molecule are going to collide. And there are several options here as far as what's going to happen. First of all, we know they're going to collide, so that's taking care of the first point. But they could collide, and if there is a reaction, then here's your AB molecule right there. Here's an AB molecule, and here's another AB molecule, and they are on a path to collide. And if they collide with enough energy, here they're colliding right here in this middle section. And if they collide with enough energy, you'll notice that the two A atoms, this is A, this is A, this is B, this is A, this is B, the small one is A, they hit with just enough energy and the right orientation. Bonds are broken between the A and the B for both of these molecules, and the two A molecules are going to be bonded together to make an A2 molecule. And the two B molecules are going to bond together after breaking from their respective A molecules or A atoms, and you're going to have two separate B atoms. So this is going to turn into what? What happens? You're going to have a molecule of A2, that is, each A atom from the two different molecules now are bonded together to make A2, that's a molecule, and then two separate B atoms. The B's are going to hit, but they're not going to bond together. They're just going to break free from their A atoms and go their separate ways. So you have two different B atoms. And this is the product of this particular collision or reaction. Okay? Now, if they don't collide, let's say the collision is too gentle, not enough energy, not enough, impact. Well, then they just bounce off each other and they go on their way. Notice you have AB and another AB. Then they collide, but it's just not strong enough of a collision to break the bonds. And after the collision, you still have AB and AB. Nothing has changed. Okay? Or what else could happen? Well, AB and AB, two different AB molecules could collide, but if they don't hit the right orientation, then when bonds may be broken, the A from each of the different molecules don't have the chance to bond because the orientation is just not correct. And so they bounce off each other and just go on their way and stay as two separate AB molecules. No reaction occurred. So in the middle diagram, there was a collision, but it was too gentle. In the third diagram here on the right side, there was a collision, which again is necessary, but they didn't collide at the correct angle in order to give you the product that you were anticipating. So there's a poor orientation. Only if there's a strong enough collision, enough energy, and the favorable orientation or angle are you going to get the result that you want. And that result here is A2 plus 2B. Notice that this is a reversible reaction, meaning that A2 and 2B's, if the orientation and the collision happens kind of again, but in the sense where the A the A2 molecule, that bond could break, and you could go back to forming your AB molecules, your two AB molecules. So this is a reversible reaction denoted by the two arrows pointing either direction. Okay? Now, how fast a reaction occurs depends on several things. Obviously, you can imagine in order for these collisions to occur, if you speed up the number of collisions, the reaction is going to happen more quickly. That's the basic idea. So what are some things that are going to affect how fast a collision happens? That's what we mean by reaction rate. So the second point here that we want to talk about is are the factors, all the factors that are going to affect how fast a reaction occurs. Okay? Let's look at them. Number one is the nature of the reactants. Well, all that means is some things react faster than others. Substances vary greatly in their tendencies to react. Some things react slowly, some things react fast. That's just the nature of what you have. Some substances take a long time to break bonds. They require a lot of energy to break bonds. Maybe the bonds initially are so strong that you just can't, break them apart to form new substances and new products. Whatever the case, that might be a result just of the nature of what you're using, nature of the reactants in the potential chemical reaction. Number two, surface area. What that means is, remember they have to collide. Well, if you don't have a lot of area for particles to interact, then there's not going to be a lot of collisions. So if you increase the surface area, okay, increasing the surface area so that particles can get in there and interact and collide, you're going to increase the rate of the reaction, okay? So the reaction rate depends on the surface area. That boundary area, it says a boundary here, that boundary area, that area between the two substances so that they can interact and collide. If you increase that, and one way to do that is to cut the substances down into small pieces so you can get in there and have the particles interact better, okay? It says here, a powder, if you make something into a powder, it's going to react more quickly because it has a greater surface area. Number three, temperature. Collisions, if they have to have enough energy, if they're traveling faster, the particles are traveling faster, they're going to hit with greater energy. Well, how do you increase the speed at which the particles are traveling? You increase their kinetic energy by introducing more energy, heat, to those particles. So if you increase the heat, introduce more heat, temperature is going to go up because the kinetic energy is increasing because the velocity of those particles are increasing. Now they're going to smash into each other with greater force and greater potential for the reaction to occur. So for collisions, okay, the collision, it has to be, as I mentioned, two particles must collide. Well, if you increase the temperature, you are increasing the average kinetic energy, and therefore the reaction rates increase with increasing temperature. Okay? Number 4, if you want a lot of collisions, why not just put a lot more particles in there, a lot more of the substance together? It's like packing a room full of people. You're bound to bump into somebody. Okay? So concentration, more particles means what? More collisions. And therefore, if you have more collisions, the potential, the possibility, the probability that you'll have some of those collisions resulting in reactions is going to be greater. Okay? So reaction rates increase with increasing concentration. And then the 5th one here is called a catalyst. Now, a catalyst is a separate substance that in one way or another helps the reaction that you're trying to occur, trying to make happen, speeds it up. It helps it, okay? It's kind of like a third party that's going to bring two people together and introduce them. So a catalyst is a substance that changes the rate of a chemical reaction, but that catalyst is not consumed in the reaction. You can use it over and over and over again. It's not going to be consumed. Okay? So for example, a metal surface, if you introduce a catalyst that's a metal, that metal might provide a surface on which the reaction can occur. And that's going to help other particles meet, and on that surface there's going to be a reaction that occurs. That particular catalyst is helping things get together, helping them collide, and helping the reaction speed up. Okay? All right. That basically is what I want you to know. This here was from chapter 17. Okay? That's what I want you to know from chapter 17 is what a reaction rate is and the things that influence a reaction rate. Okay? Now, chapter 18, we're going to come back and talk about chemical equilibrium. And we're going to go in a little more depth in chemical equilibrium. Okay? So the first thing I want you to put down chapter 18 here, and we're going to talk about equilibrium. First thing you need to know, some reactions favor products and others favor reactants. What that means is, remember we have a double arrow. Remember that double arrow is showing you that the reaction can go both directions, but rarely, sometimes, maybe I shouldn't say rarely, but you know, probably more often than not, there's going to be more of one side of the substance versus the other side. So products might be really big, reactants might be, you know, very little. You might have very few reactants when you reach equilibrium, or you might have lots of reactants and very few products. So this double arrow can be misleading. It looks like they're both, you know, going the same direction with the same emphasis, but that may not be true. You may have a forward direction, all right, that is initially pushing greater in the forward direction and then not as strong in the reverse direction. And then once you do reach equilibrium, the two directions are happening at the same rate. But once you've reached equilibrium, you might have a lot more products than you have reactants, or you might have a lot more reactants than you have products. It just depends on the particular reaction. Okay? So here's what I want you to know. We're going to be looking at reversible reactions, reactions that can occur both directions. Reactants can turn into products, products can turn back into reactants. Okay? And all reversible reactions, this is crucial, all reversible reactions will reach equilibrium. Okay? What does that mean? They will reach equilibrium, which means over time it's going to get to a point where the forward reaction and the reverse reaction are equal. And once that happens, the amount of reactants and the amount of products is not going to change dramatically. That's how you know you've reached chemical equilibrium. The reaction rates of the forward reaction and the reverse reaction are the same. Let me repeat that. It is the reaction rates that are the same. Once you've reached equilibrium, when reactants turn into products, then products, the same amount of products are turning back into reactants. Okay? Somebody leaves the room, somebody comes back into the room. Somebody else comes into the room. You have an equal number leaving as an equal number coming in. Okay? That may not happen initially when the reaction first happens. You might have a lot of people leaving the room, a lot of reactants turning into products, but then over time, you're going to have the same number going in and out, and then the number of people in the room is not going to change very much, and the number of people out of the room is not going to change very much. Doesn't mean that they're equal, the number of people in the room and out of the room. It just means that the number, the concentrations in the room and out of the room are not going to alter much, because every time somebody leaves the room, somebody comes into the room. Okay? Every reversible reaction will reach equilibrium. Okay, so here we have a reversible reaction, and I'm going to explain exactly what all these letters are representing. A and B are representing your reactants, whatever they are. Okay, A and B are just general letters that are representing the reactants. C and D are representing the products, whatever they are. Okay, whatever those are. Now, N, small m, small x, and small y are the coefficients. So X, Y, N, and M are your mole coefficients. Those are telling us how many moles are reacting of each of our reactants and products. Okay, those are the coefficients. 1, 2, 3, 4, 5, whatever. It's giving us the mole ratio in the reactants. Okay? Now, when this occurs, let's say initially we only have reactants A and B in our container. Okay? Excuse me. So let's say here that initially we have only A and B. Well, that means this forward reaction is going to occur because there's no C and D to go back the other direction. All we have right now is A and B. Okay? So the rate of the forward direction is high. Okay, this is a reaction rate. And this top dashed curve is for the forward reaction. The forward reaction is happening quickly. That's a high rate of reaction because you've got lots of A and B and they are colliding. And they're turning into C and D. But as the amount of C and D increases, then C and D can start to collide, and they can start to increase their rate of reaction of turning back into A and B. So look at our two reactions here. You see that this is A and B turning into C and D, and down here it's C and D turning into A and B. It's the reverse. It's the opposite. Okay? It's flipped. So you'll notice that initially the rate of A and B turning into C and D is high, and the rate of C and D turning into A and B is low because you're starting with only A and B. But as more C and D are produced, they can turn back into A and B, and that rate of reaction starts to increase. And the amount of A and B decreases because it's turning into C and D, and that's going to decrease until you get to a point where the two rates are exactly the same. Listen carefully. I'm not saying the amount of A and B, the reactants, is equal to the amount of the products, C and D. That's not what I'm saying. I'm saying the rate at which these two directional reactions are occurring is eventually going to be equal. They will equal each other. The forward rate and the reverse rate are going to be the same, and that's when you've reached equilibrium. And the amount of AB will not change. The amount of CD will not change once you've reached equilibrium. Okay? Now, it would be nice if we had, I don't know, just some number, a value that kind of gave us an indication of once we've reached equilibrium, where are we? Do we have lots of products at equilibrium? Do we have lots of reactants at equilibrium? Or do we have kind of the same amount of both? What do we have most of once we've reached equilibrium? Because remember, once you reach equilibrium, the concentrations of your reactants and the concentration of your products are not going to change. Okay? So, back to my analogy about people in the room and out of the room. Let's say initially everybody's in the room. Well, what's going to happen? Of course, some people are going to leave the room. The reaction rate or the rate at which people are leaving is going to be high initially. But as you get more and more people out of the room, maybe some begin to come back in. Okay? So now your reverse reaction begins to pick up until you get to a point where the people realize just the right number of people in the room. It's not too crowded, it's just the right number. And when that happens, when one person leaves, one person comes back in, and the two rates are the same. Well, it would be nice if we had a value that tells us, are most people in the room or are most people out of the room once we've reached equilibrium? Once the two directions are equal, where are most of the people? In the room or out of the room? Because once we've reached equilibrium, the numbers are not going to change. I'm not saying that people aren't going to keep moving. They will. It's called a dynamic equilibrium. They will keep moving. It's just that when one person leaves, another person comes in. And so the numbers don't change. Okay? Well, we do have a way to calculate a value that shows us, do we have mostly products or reactants at equilibrium? Do we have mostly people out of the room or in the room at equilibrium? It is called the equilibrium constant, and it is a unique number for each reversible reaction. Every reversible reaction has its own equilibrium constant at a particular temperature. Okay? How do we find it? It's real simple. The equilibrium constant, you need to write this down. This is important. Okay? The equilibrium constant here is a ratio of what? The product of the concentrations of the substances formed at equilibrium, and it's going to be the products over the reactants. Okay, products over reactants. I'll show you exactly what I mean here. Just watch. Okay. It's a product of the concentrations of the substances formed divided by a ratio to the product of the concentrations of the reacting substances, meaning it's products over reactants. Products over reactants. That is how we're going to find this ratio, products over reactants. Okay? So what you do to get this value, though, remember our reaction up here? I'm going to rewrite it for us. Here's our reaction, Na plus Mb. Remember, N and M are coefficients. They're just numbers. Reacting to form Xc plus Yd. And again, X and Y are just coefficients. So what we're saying is this reversible reaction, once it reached equilibrium, do we have mostly C and D or do we have mostly A and B? So we just take a ratio of those two concentrations. What you do is you take the concentration of C. When you put the formula in brackets, it means concentration. So the concentration of C raised to its coefficient. This coefficient here becomes an exponent. Okay? And then times the concentration of D, the other product, raised to its coefficient. Y becomes an exponent. All over what? The product of the concentration of the reactants, raised to their respective coefficients. So concentration of A raised to the N power times the concentration of B raised to the M power. This is how you find the equilibrium constant. You must be able to do this right here, and I'm going to show you some examples. Okay? Now, let's just stop for a second, though, and talk about what this K value is going to tell us. All right? Let's say that this K value is small. If this K value is small, that means this top number is small compared to the bottom number. What if the K value is like 0.02? Well, that means you've got lots of reactants, the bottom number, compared to the products. Lots of reactants. So in this circle, the light shaded area is reactants, the darker shaded is products. So that means you've got lots of reactants, lots of people in the room, not very many people out of the room at equilibrium. The K value is very small. When this ratio is small, it means the bottom number is bigger than the top number. That means you've got lots of reactants, not very many products. What if this K value is very large? If this K value is very large, like 50, then that means this top numerator here is large, very large compared to the bottom number. Products is very large compared to reactants. Okay? And if this K value is close to 1, it means you have about the same amount on either side, in and out of the room. So this again, reactants and products, if they're pretty much the same, you're going to get a K value of 1. That's the power of this value. This K value, just by doing a quick calculation, we can quickly see at equilibrium, do we have mostly reactants, or do we have mostly products, or do we have about the same of both? Okay? So let's see how we do this calculation. Here we have a reversible reaction right there. And look at our coefficients, 1, 1, and 2. Here is your only product, and we have 2 reactants. So if we want to find our K value, we might be told what the concentrations are at equilibrium. I emphasize, this K value is only for at equilibrium. So you have to wait until the reaction reaches equilibrium, find your concentrations of each species, the reactants and the products, then you can plug them in. You don't put in the concentrations that you have initially because it hasn't reached equilibrium yet. It's still reacting, maybe mostly in the forward direction. Okay? So you wait until it's at equilibrium, then we are told, all right, at equilibrium, if the concentration of nitrogen is 6.4 times 10 to the negative third, the concentration of oxygen is 1.7 times 10 to the negative third, and the concentration of nitrogen monoxide is 1.1 times 10 to the negative fifth. Now you've got your concentration at equilibrium. Okay, these have to be at equilibrium. All right, now we can plug those in. Be very careful. Remember, these coefficients become exponents. So it is always product, the K value is always products over reactants. So what is the only product? NO. NO squared. Why is it going to be squared? Because it has a coefficient of 2. You take that concentration of NO at equilibrium and you square it to get your numerator. Then you take the concentration of nitrogen, N2, and raise it to its coefficient, power of just 1. So we are told the concentration of nitrogen is 6.4 times 10 to the negative third. And we do the same thing for oxygen. It just has a coefficient of 1 as well. Okay? So if you want, these are raised to the first power. You calculate this value right here, and you get 1.1 times 10 to the negative 5. Well, that's a tiny number. That's a tiny number, okay? That's a very, very small number. So what does that tell us? If it's a very small number, it means you have lots of reactants at equilibrium. Most people are still in the room, and only a few people went out of the room, and now the two directions are in equilibrium, are happening at the same rate, and the number of people in and out of the room are not going to change. But you've got mostly reactants in this reversible reaction, okay? And that happens for several reasons. Maybe the forward direction is not very easily happening. Maybe it takes a lot of energy for the forward reaction to occur, but very little energy for the reverse reaction to occur. Okay? Maybe it's really hard to get out of the room, but it's easy to get back in the room. You see? So when you have a tiny number like this, K is very small, it tells us the equilibrium, what? Favors the reactants. I'll put it up here. This favors reactants. This favors products. Okay? So when the K is small, we say the reaction favors reactants. When the K is large, we say it favors the products. Okay? Now, there are a few things that we can do to kind of shift the equilibrium. There are some things that are going to upset the equilibrium. So for example, let's say, take my room example again. Let's say that all of a sudden somebody brought a bunch of wonderful food and they put it outside the room. Is that going to upset the equilibrium? You bet. More people are going to want to push to go out of the room into the area where there's wonderful food outside the room. So if you start to change things then that's going to shift potentially the equilibrium. And I want to show you the things that are going to shift the equilibrium. Okay, so our point here is that equilibrium shifts can happen, and they happen to try to relieve stress. When you mess with it, if you add some stress, this is you messing with it. If you mess with it, if you alter something, then that equilibrium is going to shift to try to get back to a balanced state. Okay? All right. So we call this principle Le Chatelier's principle. Le Chatelier was I believe, a French chemist, and so the Le Chatelier's principle basically says that if a system at equilibrium is subject to some stress, meaning you're messing with it, you're changing something, the equilibrium is going to shift to try to relieve that stress, to get back to equilibrium. Okay? So here are some things that can change the equilibrium, and I'll show you what happens if you do any of these things. Number one, this only applies, the first one applies only to gases. Okay? Changes in pressure, that's the first one. If you change the pressure on a reaction, that is going to alter or affect the equilibrium position. So here we have a reaction, nitrogen reacting with hydrogen to produce ammonia. Okay? Well, you'll notice that when this reacts, we've got 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia. Let's say that at equilibrium, this is the situation, diagram A right here, okay? But now let's say that you add pressure. You push with, maybe there's a piston or something, and you push on these particles with greater pressure. Well, it's like squeezing people closer together in a room. They're going to react by maybe, positioning themselves so they still have a little space. That's what's going to happen here as well. What will this reaction do to try to create more space? It is going to shift in the direction that has fewer particles because they're all getting pushed together. And if they can somehow alleviate that stress, that extra pressure, it will do it. And here's how it does it. Look, on the reactant side, you've got a total of what? 1 and then 3 over here. 1, 2, 3, 4. 4 moles on the reactant side. 4 moles of particles. But when they react in the forward direction, they turn into only 2 moles. That's fewer particles. So if you increase the pressure on this reaction, then the forward direction is going to kick in more to produce fewer particles. It actually halves the number of particles. And if you have fewer particles, then that's going to relieve some of the pressure that you are exerting, the increase in this pressure on the reaction. Okay? So here's the key for this one. Increasing the pressure leads to the formation of the side that has fewer total moles. Let me say that again so you can write it down. Increasing the pressure is going to increase the direction that is going to produce fewer total moles of particles. So if I increase the pressure on this reaction, which direction is going to kick in? The forward direction. Because it's going to take 4 moles and turn them into 2. Fewer particles, less pressure. Okay? Increasing the pressure always is going to shift it in the direction of fewer total moles of particles. In this case, it's the product side. Okay? Number 2, changes in concentration. Well, remember, if you are going to have reactions occurring because they're colliding, if you all of a sudden introduce more particles, there's going to be more reactions on that particular side. Okay? So for example, let's say, again, my analogy of people in the room, if all of a sudden a bunch of people came into the room through the window and not the door, well, now you've got all these people, added people in the room that weren't there before, and more of them are going to start to leave than are going back in because there's just not enough space. You're going to increase the rate at which people are leaving the room because you just messed with the concentration. Remember, you're messing with this once it's reached equilibrium, okay? So this is simply saying that a change in concentration will put a stress on the system, and then that reaction is going to it's going to react in a way to relieve that stress, okay? Think of it this way. This is an easy way to think of this. Okay, I'll go back to this reaction up here. I'll write it again for you. Oops, 3, I think this was. Did I do that right? Yep. Okay, so here, let's say that the concentration of N2, this is after it's reached equilibrium. N2, the concentration of N2 goes up. Well, what's going to happen? How does it get rid of some of that N2? It's going to kick in the forward direction. And it's going to use up some of that N2 along with some H2 in order to decrease the increase that you introduced. Okay? So if the concentration on the reactant side goes up, it's going to increase the forward direction. If the concentration on the product side goes up, it's going to increase the reverse direction. Just like I said, if all of a sudden the number of people in the room increase, it's going to cause people to leave the room. If all of a sudden the number of people outside the room increase, people are going to start to come into the room. Okay? All right, third one, changes in temperature. If you change the temperature, then that's going to affect how the equilibrium shifts, the direction of the reaction here, okay? So, by the way, these first two, changes in pressure and changes in concentration, the reactions will always get back to the original K value. They'll get back to equilibrium eventually. That's what they do, and they will get back to the original K value, okay? But with temperature, they will shift, but they're going to have a new K value, just so you know. All right? Now, let's look at, let's look at our reaction here again. N2 plus 3H2 2NH3. Okay? Here's what happens when you change the temperature. Think of it either the heat, the temperature, the heat that you're adding, either as a product or reactant. If the reaction is exothermic, write this carefully. It says if exothermic, if this reaction is exothermic, I'm really not sure whether it's exothermic or endothermic. Oh, let's see here. Let's use this one here. This is they're telling us right here. So here we have NO2 turning into N2O4, and it says over here that energy is as a product. Energy is going to be released. Okay? If that's the case, if you increase the temperature, it's like adding more heat. It's like adding a product. So if this heat goes up, it's like adding more concentration of heat, just like adding the concentration of a product or reactant. What's it going to do? It's going to push the other direction. It's going to push away from that and use up some of that added heat that you are introducing to the reaction. Okay? So if heat is a product, that means it's exothermic. And if you add more heat, then it's going to go in the reverse direction to use up some of that heat. So let me just say it this way. If exo and you add heat, then the reverse direction increases. And then it's the opposite. If it's an endothermic reaction, so let's imagine here, let me just change this. It's not true, but let's just say that 2NO2 plus heat produces N2O4. Now you'll notice that heat is a reactant. This time if I increase the heat, what's it going to do? It's going to use up some of that heat and go in the forward direction. So if it's an endothermic reaction and you add heat, then forward direction is going to increase. Okay? So the idea here is that with Le Chatelier's principle, if you do any of these things here, if you do any of these three things, if you change the pressure, if you change the concentration, or if you change the temperature, the reaction is always going to shift in a way to get back to an equilibrium position. Okay? Let's look at a couple examples here. Let's look right here. Number 3 says, predict the effect on the equilibrium system in terms of the direction of equilibrium shift. In other words, is it going to shift forward? Is it going to shift reverse? Or is nothing going to happen? Now notice what we have here. We have heat on this side. This is an exothermic reaction. Heat is being produced. It's given off. So now let's see what happens here. What if, question A, what if you add more chlorine? This concentration goes up. What's it going to do? It's going to try to use some of that up. It's going to try to counteract what you're doing. Well, how does it do that? It goes in the forward direction to use up some of that Cl2. So you would put forward here. This is changing the concentration. If you change the concentration on one side, it pushes toward the other side to try to balance things out. Removal of HCl. What if you take away HCl? Well, it's going to try to replace that. It's always going to try to counteract what you're doing. So how does it replace HCl? Forward direction. Makes more HCl. Okay? Increased pressure. Are all these gases? Yep. If you increase pressure, it wants to shift in the direction that has fewer total particles. Well, let's look. On this side, we have 1 and 1 moles for a total of 2. Over on the other side, a total of 2. So it doesn't matter. It's not going to shift either way because you have the same number of particles on both sides. There's no favor in one direction or the other. So this is neither. If there was a fewer number on one side, it would shift in that direction to try to relieve some of that pressure. D, decreased temperature. Heat energy is a product. If you take some of this away, then it's going to try to replace some of that. Well, how does it replace that? Forward direction produces more. So this is going to go forward. Addition of a catalyst. A catalyst is just going to speed things up. A catalyst never changes the equilibrium position. It's just going to make things go faster. So neither. Okay? And then decrease the system volume. If you decrease the volume of something, okay, if you make this shrink, make it smaller here, basically what you're doing is you're increasing the pressure. It's like squeezing it. Increasing the pressure is going to make it shift to the direction that has fewer particles. Well, we already established that it doesn't matter. You have the same number of particles on both sides, so that's neither. Okay? And there you go. These are all talking about Le Chatelier's principle, which basically says if you mess with a system at equilibrium, that is going to shift in a direction to try to counteract what you did, try to relieve that stress. All right? And that's it. That's all right now what I want you to know for Chapter 18 and equilibrium. Keep up the great work.